and start. So last time we discussed ballistic transport and most prominently quantum point contacts. Today we will develop further concepts related to quantum point contacts, one-dimensional quantized conductance, and go deeper into the topic and look at some interesting examples. So will be another lecture on one-dimensional quantum transport. First, I start with a relatively quick overview of what we discussed last time. We considered two-dimensional electron gases. These are, once again, formed at the interface of gallium arsenide and aluminum gallium arsenide, where this triangular trapping potential for electrons is created at the interface in the conduction band. And the electrons are induced by these ionized dopants, which are spatially separated from the electrons. Now, these layers of two-dimensional electrons can have very high mobility of several million in the units of centimeter squared volt second, and their densities are 1 to 3 to the power of 11 inverse square centimeters. Those are the typical densities for these structures. And on the surface of this semiconductor crystal, so on top of this aluminum gallium arsenide level, we can put metal structures, and by applying voltages to those structures, right? Those are gates. Applying voltages to those structures, we can induce electric fields, deplete the two-dimensional electron gas completely of electrons, and if we leave a small gap in between the two gates, we can engineer this potential landscape and in the gap such that only a few one-dimensional modes, so solutions of the Schrödinger equation in this transverse direction, as in first, second, third modes, are allowed to pass in this parabolic constriction. So those one-dimensional modes essentially give rise to quantized conductance as you pass current through the confined structure. Now we're looking at the top, from the top view of this structure. Depending on how many modes we are putting through, and we can change that with the gate voltages, we can observe conductance of 2e squared over h, 4e squared over h, etc. So the formula that you cannot see here is conductance is a sum over all the channels, and the 2e squared over h, the conductance quantum. And these are the first two papers where this conductance quantization was observed in one-dimensional structures. Okay, so this was just to refresh what we talked about last time. Now I want to spend a little bit of time looking at the same quantum point contacts, but now in the nonlinear regime. Means that we apply a fairly large voltage bias. So large specifically compared to temperature. So we should distinguish the linear regime. Linear transport regime is when the applied voltage bias is smaller than temperature. And in that case, all characteristics of a device should be linear. That's why it's called linear regime. So current voltage, IV characteristics should be linear. That's because if you're below temperature, you're not supposed to be able to resolve any structure, any quantum levels in the current voltage characteristic. Now if we apply a very large bias, we should start seeing some differences. So for example, these are called waterfall plots of quantum point contact conductance. I already showed them in my introductory lecture, but just to show a beautiful plot, now I want to look in more detail at these plots. So once again, what these are sequences of current voltage characteristics, and as we go up on this plot, what we're doing is we're making the gate voltage more and more positive, and at each gate voltage we are taking an IV curve. But then we are taking a derivative of the IV curve, such that we plot di dV conductance, and that's what's plotted here. These are measurements done on gallium arsenide, aluminum gallium arsenide quantum point contacts, very clean structures, and so you see how beautiful these are, and for that reason it is also remarkable that specifically in these structures you can make such a plot without introducing any offsets between the IV curves. So naturally, as you open up the QPC, as you change the gate voltage, the IV curves line up in this waterfall plot. There are no offsets. And that is very useful because just by looking at the patterns that these produce, you can learn about quantization of conductance and maybe other things that are going on top of that. So for example, here, these are from a thesis of Sarah Cronenvet, and here she labels various plateaus with their conductance values. So for example, 1, 2, those are 2e squared over h and 4e squared over h plateaus. The first and the second spin degenerate quantized plateaus. Now, why does she call these black compressions in the curves plateaus? Because as you change gate voltage, the conductance does not change. That's a plateau, right? It's very easy. So that's how it works. So here is a plateau. Here's another plateau. Here we have some zero bias peaks going into the plateau. Here once again. Now let's turn on a magnetic field. So here we turn on a pretty large magnetic field, 8 Tesla. Now we have a different structure. Do you see the difference? So if we just focus in the linear regime at zero bias, we have 2 times more plateaus here, minus some anomalies. So now we have this another compression, which is 1/2, 1, 3 halves, 2, 5 halves, 3. So these are now spin resolved plateaus. Right? We applied a large magnetic field and we split the subbands into spin up and spin down subbands. So now we have a plateau every e squared over h, not every 2e squared over h. And you can see that from the dark regions in this plot. Now who can tell me what is the range of applied voltage bias in these curves where we can still talk about linear regime, roughly?
Which picture? The first and the third one?
Well, let's say here. This is the simplest one from that point of view.
Few microvolts.
Few microvolts. I would say a bit more.
Or few hundred microvolts. 20.
Maybe 100. So here, where the conductance curve is flat, it means that the IV curve is linear, because this is a derivative of the IV curve. So this is the range. Just by looking at this, I would say this is the linear regime, and all of that other stuff is nonlinear. So let's have a look at the nonlinear regime. And by the way, at higher temperature, at this 10 times higher temperature, maybe a bit more. Maybe this is the linear regime. So it kind of makes sense. At lower temperature, linear regime is smaller. than at higher temperature. Okay, so out of the bounds of the linear regime in here, we also have some structure, right? Just like in around zero bias. So let's look at zero field, low temperature. We have these other lines. Well, this one is very interesting, separate topic, but we have 1/2, 3/2, 5/2. So kind of half plateaus, but at zero magnetic field, but at high bias. Yeah? These are not spin resolved. There is no spin degeneracy lifting at zero magnetic field, as far as we know in these structures. So what are these? Well, okay, I also wanted to show you another way of looking at the same data. Before we discuss what those are, just very quickly, this is now a map where on this axis is a real gate voltage, and the color is yet another derivative. It's a dG dVg. So it's a derivative of conductance with respect to gate voltage. And so we took this data and we took a derivative this way. So then when you have a dark region here, it means the derivative is dG dVg is 0. Yeah? So you will get a black area here, small derivative. And at the transitions between plateaus, you will get high derivative. So in this schematic, it's very easy to see the boundaries of different plateaus. So there will be 1, 2, 3, 4, and separated by pretty much what looks like straight lines, you have these fractional ones, 3/2, 5/2, 7/2. And again, this is a special one. And now at high magnetic field, the difference that you see is that there are extra smaller plateaus appearing in between 1 and 2. You have this one. Between 2 and 3, you have this one. These are spin resolved plateaus. Yeah. So now I would like to talk about these 3/2, 5/2, 7/2. Well, they have to do with, again, nonlinear regime, so high bias applied to a quantum point contact. And in particular, a bias so high that you can say more than one subband fits in the bias window. Yeah? And that's why you have these other plateaus. You can imagine that here if you have two subbands, and what's plotted on the right side is the forward moving particles and their occupation, and on the left side is backwards moving particles and their occupation. So the two occupations that differ by the applied voltage. The two chemical potentials, particles that move forward, they are occupied to a higher chemical potential than particles that move backward through the QPC occupied to a lower chemical potential. Now, if this is the sort of linear regime conventional situation where both of these chemical potentials lie within the same subband. And the higher subband is here, and they are both above the bottom of the subband. In this case, like we derived last week, we will get a perfect conductance quantization due to the cancellation between group velocity of particles and the density of states. Yeah? And now, if one of the chemical potentials, say the backwards moving, drops below the bottom of the subband, well, you actually, if you calculate conductance, which is current divided by voltage, you will get something smaller, because effectively the voltage, now you have to count it from the bottom of the subband up. So in case that you have a symmetric bias, so half the voltage drops on the left of the constriction and half the voltage drops on the right, in this perfectly symmetric situation, in this situation you will get a conductance of exactly 1/2 of a conductance quantum of 2 squared over h. And then if you have some asymmetry in your electrical circuit, this conductance value can go up and down. And so you can derive the 3/2 using the same reasoning, 5/2, etc. Well, here's another diagram from Sarah's thesis where if you go to these different points, A, B, C, this is how the bottoms of the subbands are aligned with respect to the two chemical potentials. So A is where bias is 0, so source and drain potentials are the same, and we're just aligned with the bottom of the lowest subband that goes through the QPC. And the higher subbands are somewhere higher in energy, inaccessible to us. We are in B. Well, we are somewhere below the bottom, above the bottom of the lowest subband, and we have some finite bias because we are a little bit off axis. So we will measure some current. But then C is when we are further this way, higher bias, and we've included another subband. And so now two subbands are moving forward and one subband is moving backwards. And so in this situation, we have to use this kind of reasoning to calculate the total conductance. And it can be quantized, but not in the units of 2e²/h. And if you go back to these graphs, you will also see that while there are these compressions, they don't stick to a constant value of conductance. They shift in conductance. And that's maybe because as you apply more and more bias, the bias distribution left and right of the constriction changes. That could be the reason for them shifting like that. Now this extra 0.8, or sometimes it's called 0.7 plateau, is a very mysterious effect. Here it's called 0.7. There are many different theories surrounding it for already 20 years since it was first noticed in the traces. One idea that people had is that for some mysterious reason you already have spin-resolved conductance at zero magnetic field. Because if you look at high field traces, there is no extra plateau at 0.7, there is a plateau at 0.5. And as you go from low field to high field, this 0.7 plateau, it kind of drops and merges successfully into this plateau. So people thought that maybe you can get spins due to some interaction effects already at zero field. So I think there is no final answer on what that is, but it is a topic of scientific discussion, though lately it has subdued a bit. So people ran out of ideas, or maybe it's just some mundane explanation. Well, here's another example of a waterfall plot, but this one is, you can see it's very disordered. So this is data taken on a nanowire, not on a two-dimensional electron gas. At zero magnetic field, it looks like a mess. And this is just to illustrate for you, first of all, how unique and special two-dimensional electron gases and gallium arsenide are, that they can produce these perfectly ordered families of curves that just fall like water. And how, if you just deviate in your material space a little bit from that perfect system, this is what you get. You lose that order, and it becomes very difficult to decipher such traces. You can try with transconductance, right? Take the derivative again and plot the color scale, and well, you see some lines, maybe some structure, and you can guess that maybe that is your quantized subbands, perhaps. But then, in the case of this nanowire system, this is actually our work from Delft. What we did is by applying a large field and, remember, suppressing backscattering. So when you force electrons to kind of scatter one way rather than go back, we were able to recover some resemblance of a gallium arsenide perfect waterfall plot. So there are still some disturbances and imperfections, but you can now see the structure of plateaus in the linear regime, and you can see the higher bias plateaus at kind of half values. It's very similar overall. And in a transconductance plot, so dg, dvg, you can see these straight lines that separate the plateaus. And now this is at high magnetic field, therefore quantization is already in the units of 1 squared over h, not in the units of 2 squared over h. There are also some differences in terms of bias scales that you have to use. So if you go back here, this is all 1, 2 millivolts. So let's see if we can extract the subband energy from these plots. So I would say adding about a millivolt already brings in a second subband into the structure. So the energy scale of a single subband, or the subband spacing in gallium arsenide, is about a millivolt, or maybe even 1/2 of a millivolt. And in these indium antimonide structures, it looks like you have to go to about 10 millivolts before you enter a second subband into the structure. The energy scale is 10 times larger. In part, this could be due to a different effective mass. Effective mass in gallium arsenide is 0.067 of the electron mass, and in antimonide it's 0.015. But also, due to the confinement details in a nanowire, it could be different. Another thing for which this transconductance can be useful is when you want to study the thermal properties of one-dimensional structures. It turns out that things like thermal power, Peltier coefficients, these kind of thermal effects, they are directly proportional to dg dvg, so the transconductance. So actually, from the classical theory, thermal power is linked to dE by d mu. So how much energy system changes with respect to the chemical potential, and that happens to be the same as dg dvg. So along these lines, thermal power will spike in quantum point contacts. So associated with transitions between plateaus. And on the plateaus, there is zero thermal power. Okay. Now I would like to give you a slightly different view on these constrictions and broaden this concept to, in principle, describe quantum transport as a whole. It starts with an observation that if we just plot the bottoms of the subbands, like I did in the diagrams for the nonlinear regime, if we just plot these bottoms near the constriction, so near this point, you can just say that by confining stronger the electrons, the spacing between the bottoms of the subbands, so the quantum levels in the constriction increases, but also the bottoms become lifted. And then if this happens smoothly, adiabatically, as you enter the constriction, then I could just be able to plot the bottoms of the subbands as continuous lines going from the center of the constriction, where confinement is the strongest. Think about the saddle point potential, right? In the center, it's the strongest confined, and going out, these levels become denser, and the subbands drop. So now we plot a chemical potential Fermi level through this structure. I will just cut through these levels at different points. And so what you can think about is that in the case of this particular arrangement of levels, 3 subbands are allowed to pass through the constriction, and all these other subbands are not. And now here, out here, this is the lead, right? This is the two-dimensional electron gas, which can have thousands or hundreds of thousands of channels. But now I'm kind of describing them as one-dimensional modes with just a very small spacing. And most of those modes are turned away. They are all turned away before they reach the constriction. And then I can say all these modes, they have transmission of 0 through this constriction. And only 3 modes have a transmission of 1. And I can call them open channels and closed channels. So what I did now is very interesting, because before I told you that electrons fly in a two-dimensional electron gas, they are free gas of particles, and then they enter the constriction where we have quantized modes. But now I've connected the two regions into kind of one description, as if to think that in the lead we also have modes, and we can describe them as 1D modes. It's just that we have very many of them, and then most of them don't transmit through. So I've unified the lead and the structure. So in that language, once again, looking at the quantum point contact, I can just drop the waveguide and all the language I used before, and I can just talk about channels or modes, channels, conductance channels, and distinguish them by open, the ones that can pass in both directions, the black and the faint gray arrows going back, and the closed ones, the ones that are reflected because they don't have enough energy to go through. So then from the reservoir on the right and on the left, I have all these channels coming out, and some of them bounce back and some of them go through. That's my description. And if I want to calculate the current or the conductance through this constriction, all I have to do is I have to count the number of open channels, and I have to multiply it by the conductance quantum. And in the linear regime now, I just multiply it by voltage, because everything is linear. Current's proportional to voltage. So I just need to count the open channels. That makes it very appealing, a very easy idea, right? It's easier than to think about, I don't know, Fermi distributions on the left and on the right, and integrating over the chemical potentials. Just count the channels and multiply by voltage. Well, it turns out that we can generalize this idea to many, many examples of quantum transport. And in fact, we can derive a full theory of quantum transport based just on counting channels going through. So that approach is has conveniently can be called a scattering matrix approach, but it's also known as Landauer-Buttiker formalism of quantum transport. So there are different names, but the idea is like that. You have your physics going on here, and you can assign different properties here, and all of these properties are contained in a matrix which connects amplitudes of waves coming in to this black box and amplitudes of waves coming out, and they can come out on the other side or they can come out on the same side. So then you can talk about reflection and transmission. And so in the case of just going left and right, like in a quantum point contact, we will have a matrix which has L and R indices, but these B's, they can have several components. For example, if there are 3 channels going in, then this B will have 3 components. Or if we have 500 channels, it can be a longer matrix, and it will have these blocks. So diagonally, it's reflection, meaning that you start from left and you go back to left. And so there will be a block which is reflections. And if you start from left and you end up in the right, it's transmission. So these amplitudes T and R, they can be in a quantum point contact, which is perfect, all the T's are 1s and all the R's are 0s for the modes that go through, and for the modes that reflect, all the R's are 1s and all the T's are 0s. That's a perfect. You can have values other than 0 and 1. You can have something in between, and that allows you to describe, for example, a tunnel junction where you have some finite probability of transmission and finite probability of reflection for each channel. You can describe a tunnel junction. So the book of Thomas In, Semiconductor Nanostructures, gives this very nice example. If we just consider an S matrix, so the scattering matrix, for a single mode problem, like in a QPC with one mode, but some finite transmission. Then S matrix has 4 elements exactly, and the diagonal ones will be the reflection from the left back and from the right back, and the off diagonal ones will be the transmission modules. He derives the values of these 4 matrix elements, and basically the reflections ones have these square root 1/2 minus epsilon, and the transmission ones have square root 1/2 plus epsilon, where epsilon is parameterizing the transmission or reflection of this single mode. So for example, if epsilon is 1/2, in this example we have a perfect transmission. And if epsilon is minus 1/2, we have a total reflection. And if epsilon is somewhere in between, we have a tunneling problem. Yeah. And this approach can also be extended to more than 2 leads, where you don't just have left and right, but you have all kinds of probabilities going from 1 to 2 to 3. And you can ask yourself, what is my total probability of starting here and ending up here, but taking into account all possible processes. So then for each lead we have to define the number of channels that go in, scatter back. Well, if we know all these parameters, and the values for all the amplitudes might be determined by what's going on here, which is your physics, whatever you want. For example, in this example, we have one mode going in from this lead, and it can also reflect. One mode going in from this lead, and it can reflect. And we have 2 channels in this lead. So what will be the dimension of the S matrix? For this particular example?
4.
Yeah, it will be 4 by 4. So it doesn't matter if there are separate leads. We just have to write 4 in, 4 out. And we just count the channels, and that's it. And then probability of going from here to here, well, that's determined by what's going on inside this cavity. So that's the physics part. But the approach is very general and extendable and very flexible. So the scattering matrices, they cannot be completely arbitrary. There are some relations that you have to maintain in between the matrix elements. Has to be a unitary matrix, and if you work through the math, it translates into having a need to conserve a charge or a number of particles that go in and come out. Has to be a unitary matrix, and very importantly, it has to obey this symmetry with respect to reversal of magnetic field, right, in a non-magnetic system. So if you don't have any ferromagnet or spin-dependent scatterer, this has to be obeyed. So if you want to flip magnetic field, you have to flip these indices. So at least change them like that. That means that if you change the direction of current and change magnetic field, the transmission should remain the same in a non-magnetic system. So that's called Onsager relation, very fundamental, and it holds for multi-terminal devices, multi-channel, but you have to be careful which indices you flip. So at some level above all of this, Onzaga relation or time reversal symmetry reigns. And there is also a way to relate these somewhat abstract notions of transmission and reflection amplitudes, like in the S matrix, to real conductance values or current conductance voltage values. So again, we want to obtain a linear regime formula where current is the sum of conductances times voltage. And then these conductances, they form very naturally a conductance matrix, just like similar to the S matrix, but then now we cannot really distinguish the channels, so we just have these three leads, and conductance has to include all channels in each lead. So that is closer to experiment. This is what we would measure. We could in principle map out the entire conductance matrix for any sample just by applying voltages to different points and measuring currents. So this conductance matrix also obeys certain obvious rules which actually follow from things like Kirchhoff law. So if all the currents going into one node have to add up to 0, and that means that the sum of conductances in this matrix over each column is equal to 0. That is just a direct consequence of a Kirchhoff law. And the fact that we can arbitrarily choose a 0 voltage means that the sum of conductances over each column is also 0. So these are sort of the hard restrictions on the conductance matrix, and that reduces the number of free elements. In fact, if you have n leads, I think there are n-1 independent equations that you can write, and you have n-1 free parameters. So you can solve everything directly, exactly. And the connection between transmission and reflection and conductance goes via this Landauer formula. So let's just look at it. It is actually a very simple formula. It has this conductance quantum at the front. It's E squared over h. And then you integrate over this part, which has the Fermi distribution, so it takes into account the finite energy, finite temperature effects. And these guys are just transmissions in an S matrix, transmissions and reflections in an S matrix. So the P is a trace over the scattering S matrix elements that are relevant for going from alpha to beta. In the case of just two leads, if you have two leads, left and right, then alpha and beta can be L and R. And in that case, conductance is a trace from left to right. So all the elements from going from left to right. So it's a trace over the transmission part of the S matrix. And it, satisfyingly enough, Onzaga relation is also preserved when we talk about these conductances. So following directly from the properties of the S matrices, you can derive that in a two-terminal device, this is a very rigid constraint that if you reverse the direction of current from alpha to beta to alpha, and reverse magnetic field, the conductance remains the same. Okay, so what people do when they want to study new physics with S matrices is they diagonalize them. They find the eigenstates, they find the poles of these matrices. So the solutions can be complex, and they can have a real part and a complex part. A real part might mean the energy of a certain quantum level through which you transmit, and the imaginary part might correspond to the width of that level, so the time that you spend in that level. So that's a very powerful technique, and you sometimes might see a theory paper which just talks about S matrices all the way, and maybe at the end convert it to conductance for theorists who get lost in the S matrices. So this is a very widely used theoretical tool, and I wanted to make you aware of it without going into too much detail. But as we wrap up this section, I wanted to just think together with you about this one problem. And it's not actually directly solvable by S matrices, but we could try. But what's more, that I want you to think about it together. So this is again, two-dimensional electron gas. The dark gray is the surface of gallium arsenide, and these light gray are gates. And these people, this is from Marcus' group at Harvard, they have defined this cavity. This is a fairly large, a couple micron large cavity into which electrons can go, scatter, bounce, and leave. And the entrance and the exit are quantum point contacts. Now we have two quantum point contacts, and we are applying voltage from here to here. We're applying current and measuring voltage, whatever you prefer. And the question is, what conductance are we going to measure? So what I can tell you is that both of these quantum point contacts independently are set to the first plateau. So each of them has a conductance of 2e²/h, perfect transmission, transmission 1. And then they bounce around in this cavity and they leave. So let's think together. What's the first guess for the total conductance or the total resistance of this structure? So you have 2e²/h here. That's 12 kilo ohms, 12.9 kilo ohms. You have another 12.9 kilo ohms here. So what will be the total? Let's just think out loud. Bin, what do you think?
So I think it will be 1/2 the total.
The conductance will be 1/2 of the total.
No, conductance should be 2, the resistor should be 1/2. The 2 times.
So, okay, so first guess is that you go through here, you lose about 12 kilo ohms, and then another 12 kilo ohms here, so the total resistance will be something like 25 kilo ohms. Right? Another way to look at this is from the point of view of these transmissions. You could say, okay, now I have this example, except I have to do some changes. All of these A's are 0 and all of these B's are 1, so this one is closed, and we just have one channel coming in, one channel going out. But here we have perfect transmissions. So these are all 1s. Yeah? And so we come in perfectly, and we leave perfectly. And so actually everything depends, like I said, on what's going on here. Now there are two possibilities. If in this cavity we've lost energy, if the actual voltage dropped in here, then Bin is right. Then the resistance is 25 kilo ohms. But if we just kind of fly in and go out very quickly, and we don't have time to lose energy, to undergo an elastic scattering process, then actually, remarkably, the total conductance will still be 2e²/h. So 12 kilo ohms, even though you have to go through one QPC and then leave through another QPC. And so it's all determined by the physics that's going on here. And what would be the relevant parameter for this cavity that would distinguish the two situations? What should so once again, what should happen inside this cavity for us to get 1 squared over h?
Ballistic transfers.
Small decoherence lag?
So in both cases ballistic, that's no problem. But indeed, the relevant one is the kind of dephasing length or inelastic length, which are roughly the same concepts. So you can be ballistic, but you're just flying and then you catch a phonon, for example, and you lose your energy, or you otherwise randomize your phase. So when this cavity is smaller than the dephasing length, then transmission is perfect. All these ones just make it like one channel. And the conductance is 2 squared over h still, even though you have this cavity. And then if we start growing this cavity, even though we remain ballistic, we might exceed the dephasing length. And in that case, we will have to give up the energy in this cavity. And then we start anew. We have to add another 2 squared over h here, and the total resistance will be 25.8 kilo ohms. So I think this is an interesting example that shows that what's going on inside here determines the physics, but we can make a generic approach, generalize the leads coming into the problem using Landauer-Buttiker formalism. Okay, now I would like to make an intermezzo and talk about a very interesting and a very different two-dimensional system, and you will see the connection to what we're talking about in a moment. But this is this was briefly very popular before graphene came along, and this was explored as an alternative to these perfect two-dimensional electron gases, which not every group could get because they are require such art to produce, like MBE technology, etc. So what these people do is they have a liquid helium. It turns out that you can just inject from a needle electrons onto the surface of this helium, and they will remain trapped to the surface, forming a perfect two-dimensional layer. So you can create a two-dimensional electron gas on the surface of helium liquid. So these are called electrons on helium. Beautiful idea, beautiful technique. It turns out that they are confined pretty strongly at the surface. Confinement energies of about an electron volt, pretty high. And if you can keep the helium film very quiet, then you will get a really nice two-dimensional electron gas. The density that you can get is somewhat lower than in gallium arsenide. Remember, in the beginning of the lecture I told you that we can get 10 to the 11. Well, in these, practically, you can get something lower, a couple of orders of magnitude lower. What that means is that electrons are spaced farther apart, and they are less screened by their friends, other electrons, and that means that Coulomb interactions between electrons are much stronger than in gallium arsenide. The charges are not so well screened. And as a consequence of that, they think that if you lower the temperature of this helium, you can get from this gas of randomly flying electrons to a somewhat ordered state, which is sometimes called a Wigner crystal. Crystalline phase of electrons in free space, that's called a Wigner crystal. And they're held in this crystal by Coulomb repulsion from each other. It turns out that they prefer to stay in a crystal lattice rather than fly around. It costs too much energy. So this is such an interesting, bizarre system, and it's been studied for a few years, and people have managed to also create nanostructures kind of from these electrons. What you can do is, here is a tray of helium liquid, and these big lines are little channels, micro channels, in which helium sits very quietly without much disturbances. And then in the center here they have nano-fabricated electrodes, which are gates. So now underneath helium liquid they have electrodes where they can apply potentials. And just like in gallium arsenide, they can deplete these electrons. So electrons floating on helium here, and a gate is underneath. They can deplete, they can confine them. In principle, they can make puddles or channels. And so this group from Japan, they have tried to make a quantum point contact by having a split gate and allowing electrons on helium only in between the two gates. And what they have observed is as they change, again, like in gallium arsenide, increase gate voltage, they have observed these plateau-like structures, these modulations in conductance. So going from left to right, these kind of modulations. And this is just a derivative of this plot, so you can see better the modulations here. Now question, is this a quantum point contact? Information is in the slide for you. What's the most important property of a quantum point contact?
It's too big.
What's too big?
Well, it's like 10 microns.
Well, but if you apply a very large voltage, maybe you can confine. But something's too big. G is
the space between and protons are too small.
resistance is too big. It's mega ohms.
Yeah.
We need kilo ohms. We need 10 kilo ohms, 25 kilo ohms, something like that. This is too big. Resistance is too big. Conductance is too small. So this is not quantized conductance. This is something else. And they have recognized it because they wrote classical point contact, CPC, not QPC, in the title of their paper. And they have found a very nice explanation for these. The explanation is as follows. Basically, it all comes down to these electrons having these very strong Coulomb interactions. And it turns out it costs you energy to put two electrons at the same time through this constriction. But it's not a quantum confinement energy. It's a classical Coulomb electrostatic energy. So depending on the width of the constriction, it could be that only one electron at a time could go through this channel. And if you change the voltages, you can allow 2, then 3, then 4. So it's a little bit similar to quantized conductance, but it has no relation to any conductance quantum. It has no relation to subbands in this structure. It is just a interaction, electron-electron interaction effect. So they even go through rough numbers. These are slides from Dr. Rees from ReChem. That I got off the internet. They just take the gate voltage spacing between these plateaus, and they calculate the electrostatic energy that their electrons have, and they arrive to this gate voltage spacing, which is pretty similar to what they measure experimentally for how much voltage does it take to add another electron through this constriction. So when I heard his talk in person, he compared this effect to people in a subway, for example, trying to go through a narrow door altogether. So they, depending on the size of the door, there could be some quantization effect where first only one person can go through the door at a time, then two people at a time. If the door is bigger, three people at a time. It's not quantized, but it is modulated with a number of people. So an effect very similar to a QPC, but not a QPC. And I think a beautiful electronic system. You can also guess it is that it would be harder to create quantum confinement structures with these electrons, because these are real electrons. They are not effective electrons like in a crystal. So they have a mass of 1 compared to gallium arsenide mass of 0.067. These are much heavier electrons, so their wavelengths are much smaller. And that's why the actual quantum confinement energy is pretty small.
And also the Coulomb interaction is quite big here, so there's no way you can treat them as the body-state motion.
Oh, that's yeah, I guess electron-electron interaction will lead to many scattering events between them. Yeah, I think that's true. I don't know what the mean-free path is. This is something to look at by maybe studying archive on the topic of these electrons. Okay. And the last part of the lecture, I want to focus on the spin effects in quantum point contacts. It is all based on once again, applying magnetic field. This field is applied in the plane of the 2-DEG, so there are no orbital effects like in focusing experiments. This is just adding a Zeeman energy to the electrons in a 2-dimensional electron gas. And what you see, once again, the conductance used to be quantized in the units of 2e squared over h, and when you apply magnetic field, these extra plateaus appear at 1e squared over h. And what I want to tell you is that it is very interesting to think about just living at this one plateau, because when you are here at this plateau, what happens to the other electrons? Well, if you are the up electron and the field is up, okay, you can travel through the subband, but if you're a down electron, your subband is at a higher energy, so you are not allowed to go through. So you scatter back. So if you apply voltage to a quantum point contact, which is tuned to this regime, to this first plateau at 1e squared over h, you can only pass electrons over one spin orientation along the field. So the other electrons are reflected. So you have created a perfect 100% spin filter. You have electrons of both spin, you apply voltage, and only electrons of one spin pass. So on top here I show the electrons of just a green color, spin up. There could be, if we keep passing this current, and we do it very intensively, we can actually saturate this region with just spin-up electrons. We can create an excess of spin-up electrons. We can polarize dynamically, non-equilibrium, 2-dimensional electron gas outside the QPC. So we can operate a quantum point contact as a spin filter, a spin injector. So that's very neat. Another thing to realize is that much the same way, this kind of polarized quantum point contact can be a spin detector. So imagine that on the left side of the QPC we have an excess of spin up. Maybe we created it by another QPC. And what that means in terms of chemical potentials is that for spin up electrons, the chemical potential is higher than for spin down electrons, because there are just more spin up electrons. So in this non-equilibrium situation, we can think about imbalance in chemical potentials of spin up and spin down. And now this constriction can only pass spin up, cannot pass spin down. Well, spin up electrons will keep going through, and here we have an infinite reservoir. So after some time, spin up electrons will relax and become spin down electrons. But more and more spin up electrons are coming. And the spin down electrons cannot go back. So over time we will start building up extra charge behind here. This was done back in 2002 in this beautiful experiment, which you will already recognize. It's a focusing setup. Like from last lecture, there are two quantum point contacts, E and C, emitter and collector, and the electrical circuit is non-local, so current is sent this way, ground is here, and voltage is detected on the right side. And when we apply field out of the plane, we focus electrons from here to here, and all the trajectories, no matter what angle, come here, just like it's shown here. So for the first trajectory, we get the first peak when electrons coming out of here exactly hit the other constriction. For the second trajectory, we get the second peak. There's a third peak. And now we will apply a second field in the plane. So this field does not affect this spectrum of trajectories because it's perpendicular. But it does introduce Zeeman splitting, and this field will be much larger than this field. This field will be 10, 100 millitesla, and the in-plane field will be Tesla. So we will set the field such that the quantum point contacts are spin polarized, and then we will compare these focusing curves for different settings of the quantum point contact. So when both quantum point contacts are open to 2e squared over h, means both spins can go up and down, 2e squared over h, means that we get a baseline curve, which is a dashed line, which is a little bit low here. Now, when we polarize one of them, so these correspond to these 0.5s, then the level of the signal changes. So when both of them are polarized, you get a very high signal. And when one of them is unpolarized, you get a lower signal. And so from looking at these little differences here, they were able to deduce that indeed, by the end of the day, there is some spin polarization injected and collected in this quantum point contacts. Actually, the reason why I showed you this graph is, first of all, to connect to what we studied last time, magnetic focusing in a ballistic system, but also to say that this is actually maybe not the best way to look at spin properties, because you always have a signal and you're just looking at the small changes in the level of signal. So there is a better way. And that is called a non-local spin valve. So it turns out that to look at these spin accumulations, it is better to go not to a ballistic regime but to a quasi-ballistic regime. The experiment is very similar. You have a quantum point contact injector, and here you have a detector, but now you're not sending electrons like that. First of all, you've confined the channel from the top such that they have to bounce many times to go from injector to detector, and you're also routing them actually this way. So electrical circuit is like this. The electrical current goes left, and it can carry spin polarization, and we are measuring here completely non-locally on the right side. So ideally there should be absolutely no voltage here, because all the electrical current is flowing on the left side of the circuit. Yeah, so this one is floating, so the charge potential should be 0. Unless, of course, there is a spin accumulation. So this is now the chemical potential diagram of the non-local spin valve. You have the injector and a detector, you have two reservoirs left and right, and in this quasi-ballistic channel you have kind of different circuits for spin up and spin down. And let's look at these chemical potentials. This is the injection point, and at the injection point we're sending in spin ups. So we are sending so many spin up electrons that we are creating a chemical potential difference between the spin up electrons and the spin down electrons. Now the average chemical potential, the average one, remains at this level, and the two spin species, if you break up the average into two spin species, you start getting this difference. Now let's look at the left side. This is the side that's grounded electrically, and therefore you have the average chemical potential dropping linearly, because this is now a quasi-ballistic, so sort of a diffusive regime. So we don't have these ballistic non-dissipative trajectories, so we just draw classically the chemical potential dropping linearly. On the right side, like I said, the average remains constant because there is no voltage drop, charge voltage drop along this structure. But what happens on top of this is that spins diffuse out of the injection point, and their difference becomes less and less because they intermix. There's a counter diffusion of unpolarized current from here. There is some spin relaxation, and so as you move farther and farther from the injection point, the difference between spin up and spin down becomes erased. And so the two of these come together, and eventually they reach zero at the reservoir. Now if we put somewhere here or here a detector, remember we will be sensitive to this voltage difference because quantum point contact will be spin polarized again. So we can actually detect a voltage even though the average chemical potential does not do anything. So this is what is done. A little bit difficult to see, but you can see this blob, right? So this is a complicated plot, but on the side panels you have the conductance traces for the detector and the injector. And these yellow regions correspond to 1e² plateaus when the injector and the detector is polarized. And what's plotted here is the non-local voltage, the voltage across the detector. So this non-local voltage is very high when both the injector and the detector are polarized. So when we inject spins, create the difference in the chemical potential, and then we detect that difference in the chemical potential non-locally. And then when one of them is unpolarized, either the injector or the detector, there is no voltage, absolutely no voltage. So now you can see that in contrast to the focusing experiment, where we always seen a focusing signal and just the difference was in the magnitude of that signal, now there is either signal or no signal whatsoever. So this is a very interesting example that shows you a quasi-ballistic transport, spin properties of quantum point contacts, non-local measurement, and the power of non-local measurement in this case in separating spin and charge. Yeah? So this is why I draw here a pure spin current without any charge. Just a spin degree of freedom is doing something on this side. And here charge and spin current, where charge and spin signals are mixed. Hard to separate. Okay, you can do this measurement as a function of magnetic field and see how the non-local spin voltage turns on as a function of field. So as this 1e² plateau develops and grows, the non-local spin signal increases. And so by means of this spin current measurement, you can calculate the spin polarization coming out of this plateau. So especially interesting to study this transition region where the plateau is just forming, and what you can see is that the polarization is not 100%. And when it reaches this flat region, it's when the plateau is fully formed and the spin polarization is 100%. So this is the schematic concept of a non-local spin valve, electrical non-local spin valve. You ground the left side of the device and send the charge current that way, and you send it through a spin polarized contact. And this contact creates excess spin polarization in the wire, and that spin polarization is diffusing left and right, but especially on the right side, it's diffusing in the absence of any charge signals. But it can still create a voltage if this contact is also spin sensitive, also spin polarizing, and can only pass the blue spin. And this concept was not, once again, like with many other experiments, was not for the first time done with two-dimensional electron gases. It was done already in the 1985 with just metals, and a little bit later with nanostructures. This experiment, you can see an aluminum wire with two cobalt electrodes. So cobalt is a ferromagnet, very similar to quantum point contacts. You can create spin polarization by sending an electrical current through a ferromagnet. So the nature of this arrow can be anything as long as it spin polarizes. And so you can send the current through cobalt into aluminum this way and measure a voltage here. So this is exact same experiment as I just explained with 2DECs, but now with ferromagnets and metals. The dimension of this structure is, here it's about 500 nanometers, and with 2DECs it was 100 microns. And that is the difference between diffusive transport and quasi-ballistic transport. You can extend the spin diffusion lengths and all these things by several orders of magnitude. So that's a nice feature. Okay, I think we should stop here. Thank you.